In this video, I want to look a little more closely at row echelon form and the number of non-zero rows in the row echelon form, which is called rank, and then a special case of row echelon form, which is called reduced row echelon form. So last time we ended up with the row echelon form matrix 1, -1, 2, 1, 0, 1, -6, 4, 0, 0, 1, 1, and then a row of all zeros. A natural question to ask about row echelon form is, if two people do row operations in different orders, do they get the same row echelon matrix? Because we just had a list of operations and there was no rule saying that we had to do one operation and we had to do another operation. So two people might do them in different orders and might get eventually a row echelon matrix. Are they necessarily the same? The answer is no. They're not necessarily the same. If we start with the matrix above and we do row 2 becomes row 2 plus row 3, then we get, let's see, row 1 stays the same. Row 2 becomes 2 plus 3. So 0 plus 0, 1 plus 0, -6 plus 1 is -5. 4 plus 1 is +5. 0, 0, 1, 1. So we get another row echelon matrix, but it's not exactly the same one. It doesn't have exactly the same numbers in it. What is the same is that the leading ones in each row are going to be in exactly the same places. In other words, the number of non-zero rows is the same. Even if not all the entries are the same, the number of non-zero rows is definitely going to be the same. We call this number of non-zero rows the rank of the original matrix. Now, of all the different row echelon matrices that you could get from an original matrix, there's one that's very nice in that, in addition to having zeros below all the leading runs, you could get zeros above all the leading ones as well. So a very nice row echelon matrix has 0 above, so not just below, all leading ones. And this is called a matrix in reduced row echelon form. And we can get to the matrix in reduced row echelon form by taking the original matrix and just doing more row ops. So do more row operations to get it. So if we want to have zeros above this 1, we could add 6 copies of row 3 to row 2. And we could subtract 2 copies of row 3 from row 1. 6 copies to get rid of this -6, and subtracting 2 copies to get rid of the positive 2. So let's say row 1 becomes row 1 minus 2 times row 3, and row 2 becomes row 2 plus 6 copies of row 3. Again, I'm going to do 2 row operations at the same time, which is living dangerously because it's more easy to make mistakes this way, but I'll try and be careful. So if we take row 1 minus 2 times row 3, we get 1, -1, 2 minus 2 ones is 0, 1 minus 2 ones is 1 minus 2, which is -1. And then 2 becomes 2 plus 6 times 3. 0, 1 plus 6 zeros is 1, -6 plus 6 ones is 0, 4 plus 6 ones is 10. 0, 0, 1, 1, 0, 0, 0, 0. Now this one, which had zeros below it, also has zeros above it. This one, which has zeros below it, still has something non-zero above it. But we can fix that if we take row 1 and add row 2 to it. So row 1 becomes row 1 plus row 2. And we get 1, -1 and 1 is 0, 0 and 0 is 0, -1 and 10 is 9. And then copy the other rows, 0, 1, 0, 10, 0, 0, 1, 1, and all zeros. And now every leading 1 is the only non-zero entry in its column. It has all zeros below it and all zeros above it too. This is not a leading one because it's the second one in this row, so that one does not need to have zeros above it and below it. In fact, it's not always possible to do that. It's possible to do it for the leading one in each row, but not necessarily other ones. And this matrix has reduced row echelon form. The end.